this is on page 44. And we're going to start off with looking at x squared minus 2x plus 1. Here it is. It's a parabola, which when you factor it is x minus 1 squared. And using your transformations unit, does it make sense that that would be a parabola shifted 1 to the right? Okay? Now, when we factor this, if I had started with this form of the equation, x squared minus 2x plus 1, if I factored it, both of these factors end up being the same, x minus 1 and x minus 1. So it means I have only one x-intercept, but technically, when solving, that solution shows up twice. The wording that we're going to use for this is we're going to say that this has a 0 of multiplicity 2, because it's the same one, but it happens twice. Okay? And that multiplicity is going to be important because it changes what happens at that x-intercept. So for graphs at x-intercepts, sometimes, like the graph that we just did, something like this, notice how it went straight through each of those points. That's the graph that we just did after it was factored. Sometimes your graph goes straight through your x-intercepts, but on this parabola, your graph bounces. So we're going to make a little note off to the side here. It's going to talk about multiplicity, and we're also going to take out our highlighter. We're going to highlight this idea of multiplicity. And our note off to the side, even if you have an even multiplicity, this is not a mathematical word, but it describes what happens. The graph bounces at the x-intercept. So if we have an even multiplicity, like this one happens twice. If a factor happens 4 times, if a factor happens 6 times, we would say this is our 0, and it has a multiplicity of 2. Then when we get to that 0, the graph bounces off of it. Odd multiplicities there are 2 things. If the multiplicity is 1, this is what we've been dealing with mostly so far. The graph goes straight through that x-intercept. So all the graphs we've had so far have all had multiplicities of 1. And when we draw our graph, we just went straight through that point to the next point, because that's what would be natural to go through all the points. Anything bigger than 1, any odd multiplicity bigger than 1, here your graph is going to, sometimes people like to say it bends. Sometimes people like to say that it flattens out. And we see this in this x minus 1 cubed graph. Like this g of x graph is technically, if it's cubed, you have x minus 1, x minus 1, x minus 1. If you had factored it 3 times, you would get x equals 1 as the solution 3 times. we would say that that 0 has a multiplicity of 3. Now you know what the x cubed graph looks like from our very first unit. An x minus 1 cubed would be that x cubed graph shifted 1 to the right. But now, at this x-intercept, the graph actually, and sometimes people, the flattened out thing, sometimes people draw a tiny little flat line there. Because the graph flattens out at that x-intercept. And then when you go to graph it, you have to join to that flat line, go through that flat line, and that creates a bend in your graph. But it's not just a little, it's a bend enough that it flattens out. And that's how we deal with odd multiplicity. So now, when we're graphing, if we look at our strategy for graphing, which we wrote down in the last example, use the intercepts and the end behavior to graph. We're going to use the intercepts and the end behavior to graph, but now we also, in the intercepts, have to consider the multiplicity. So example 3 is actually easy because the factoring has been done. They took the, I think the long part of this question is the synthetic division and the factoring. It's not hard, it just takes a while. So this one, the factoring has already been done. Because it's already factored, the end behavior is a little bit trickier. Why? What kind of graph is this? Is it an x to the 4, x to the 3, x to the 5, x to the 6? What kind of graph is it? If you had to find out, you'd have to multiply it all out. Can you just think about the first one? If you look at the first ones, can you see that the first one and this one to the power 4 would be an x to the 4? Right? This would be an x to the 4. And this one, well, it's an x minus 2. If you multiply those together, you see that you would get a positive x to the 5 graph. So as far as our end behavior, it's odd. It's going to act like a line. We know it starts down here and ends up here. Next, we always found our y-intercept. Y-intercept was easy because you plug in 0 for x. But now you have to be careful because it's not just the last number. If it's already factored, if I plug in 0 here, I'm going to get 1 to the 4, which is 1. If I plug in 0 here, I'm going to get negative 2. Negative 2 times 1 is negative 2. You have to always plug in 0 for x. But because it's factored, our x-intercepts are easy. We're going to have an x-intercept at negative 1, and we're going to have an x-intercept at 2. One of them has a multiplicity of 4, the other one has a multiplicity of 1. So when I go to graph part A, I can label my y-intercept 0, negative 2. I can label my two x-intercepts negative 1, 0, and 2, 0. I know that my endpoints, my end behavior, has to start down here and end up there. And before I go and draw this, I'm also going to make myself a note that I know that this one, that one's going to be the bounce because it has a multiplicity of 4. And this one has a multiplicity of 1. Now you're not going to write those things down, but you're going to think about them. Because now when I go to draw my graph, I'm starting down here. When I get to this one, I have to bounce, and it has to be a rounded bounce. Okay? Sharp point is going to lose you a half a mark for shape. Polynomials are always rounded. So some people actually do this. They're like, to set themselves up, they make a nice rounded corner there, make a straight line through there, because that's what's going to happen. Now, when I go to connect, I connect to there, come through, connect to this, keep going. And I don't have to worry about when I'm doing my flow, all of a sudden like, oh yeah, I'm supposed to bounce, and then your bounce gets really sharp because you've only thought of it at the last second. So if you draw that bounce first, you draw that straight through, that can make your life a little bit easier. Okay, so same thing. Part B. What do we have? We have, I'm going to just rewrite it here. Negative x plus 1 cubed x minus 3. Okay? So if I'm thinking about what kind of graph this would be, I have an x here, I would have an x cubed here, and I have a negative out in front. Oh, it's going, sorry, I have a typo there. X cubed times an x would give me an x to the 4 graph. Does that make sense? Because I have an x here and an x cubed here. Together, x times x cubed will give me x to the 4. And this is positive, but I have a negative out in front, so positive times a negative would give me a negative. So my end behavior, I think of a parabola opening down. There's my end behavior. My y-intercept. I'm actually going to show the work where I plug in 0 for x. You see that this is going to be negative, this is going to be 1, and this is going to be negative 3. Negative 1 times negative 3 is positive 3. Be very careful with y-intercepts when it's in this factored form. It's the number one, like, it's just simple mental math. However, it's the number one mistake students make. They make a mental math mistake finding the y-intercept, and then when they go to graph, and this is usually a way that you can tell you screwed up. If you label your x-intercepts and y-intercepts, and you label your end behavior, and you label your bounces and straight throughs and bends correctly, and you try to graph it, and it just does not, it's not possible to go through all the points and do what you're supposed to do, it means you made a mistake. Do not make up a new mistake to counter your old mistake, because you've made one mistake already which has lost you a mark. Then if you make up a new mistake to try to fix it, that loses you another mark. So take a breather, go back and redo everything, but slower is the best strategy. Okay, so I've got my y-intercept. My x-intercepts, and this is where it's nice because it's already factored. We have, from the first factor, negative 1 comma 0, it would have a multiplicity of 3. And we have 3 comma 0 with a multiplicity of 1. So we go to graph, and I'll just put it off to the side here. Our y-intercept was at 0 comma 3. X-intercept of minus 1. And it has a multiplicity of 3. So we need to show that bend or that flattened out. So what I'm going to do is I'm just going to draw a tiny little flat line there to remind myself that one needs to flatten out. And then at 3, this one is going to be straight through. I'll draw a little straight through line there. Straight through ones, you don't have to add the extra line there. You'll figure that out when you go to graph it. But now, where is my end behavior? We got to start here. Oops, I'll put blue. Just down here and down here. Circle those. That's my end behavior. So what do I have to do? I have to come up. I see this flattened out, so I join to one side, I come through the flattened side. I've got to go through here and then straight through. Again, my maximum I kind of put somewhere in between those two x-intercepts. So when I hit my y-intercept, a lot of students just want to start going down right away. If it wants to be smooth, it would probably go up a little bit higher than that to come down. And there we have our graph. It has the bend, it has the straight through. Ones you can circle on this one are 9, 10, 11, and 12.